Thanks for coming in, and I'd like to introduce you to Anya Scuderi. She is with a company called Deep Fission, and they are, let's see, so they have a part of our impressive afternoon lineup here. She's going to be presenting Powering Humanity from a Mile Underground. She specializes in strategic finance for energy engineering ventures. So let's have a hand for Anya Scuderi. Thank you.
Hi guys, can you hear me well? Okay, perfect. All right, so thank you for the introduction. Again, I'm Anya Scuderi, and I'm a Director of Strategic Finance at Deep Vision. I would like to thank Energy Fuels for hosting this wonderful event and for inviting me to speak in front of all of you. I'm very excited to share what we are building at Deep Vision. So excited that I only got 2 hours of sleep last night preparing. I'm kidding. But before I tell you what we are building at Deep Vision, I'd like to take a little time to share a bit of my personal story and how I ended up here. And my story begins in Ukraine, where I was born and raised. And like many Ukrainians of my generation, I grew up in cultural aftermath of Chernobyl. Although I didn't understand what that meant as a child, I absorbed the belief that nuclear energy was something dangerous, something to fear. It wasn't based on any technical knowledge. It was simply how everyone else around me felt. I immigrated to the United States about 20 years ago. I studied finance, and after graduating, I joined the renewable energy sector. I was proud to be contributing to clean energy and apply my skills to a field that I thought was world-changing. As a finance professional, I love the complicated financing structures we use to structure large energy infrastructure projects. But at the time, I didn't think much about the electrons behind the numbers. Then in 2022, everything changed. When Russia invaded Ukraine, my home country, the energy issues I'd followed from distance suddenly became personal. And I was drawn deeply into the web of European energy policies, not just as a Ukrainian, but someone who saw how energy choices impact geopolitics and global security. And in the center of it all, I kept coming back to nuclear energy. I decided I want to understand it. So I started reading nuclear energy history books, trying to educate myself on the fundamentals of reactor physics, and talking to industry professionals. And what I discovered surprised me. I learned that not only nuclear energy is clean and extremely safe, it is also the most reliable and efficient way to make power that we have. And of all the amazing attributes of this technology, the one that captivated me the most was energy density. The fact that a tiny amount of uranium fuel can generate millions times more power than any other source. That was and still is mind-blowing to me. And with this realization, I found myself asking, why are we not building more? And that was a career-changing point for me. I decided to leave the renewables, join the nuclear industry, and committed myself to solving real barriers holding nuclear back. Not theoretical problems, but practical challenges of construction, cost, siting, regulatory timelines, and supply chains. And that's what led me ultimately to Deep Vision and what brought me here today. And I'd also add that it's especially meaningful for me to be here at White Mesa Mill. The uranium produced here represents the very first step in powering future deep fission reactors and our country's nuclear future. And as someone who watched my home country invaded by the same regime that still today supplies nuclear fuel to many US reactors, well, this mission here feels deeply personal. And I'm thankful for the leadership companies like Energy Fuels have shown in rebuilding secure US-based nuclear fuel supply chain. Now, what is deep fission? Deep Fission is an advanced reactor technology company. There we go. And we are designing a light water, small modular reactor, 15 megawatts, but to be deployed in a radically different way, deep underground, in about a 30-inch wide borehole, 1 mile beneath the surface. Now, this crazy idea originated at our sister company, Deep Isolation. And what Deep Isolation does, they use deep boreholes for spent nuclear fuel disposal, also known as nuclear waste. And while modeling hypothetical risks there, the team asked, what if, instead of spent nuclear fuel, we accidentally end up with fresh fuel underground? Could a nuclear chain reaction occur? And the answer at first was no, but it sparked deeper research. And it turns out that under the right conditions, the right pressure, geometry, thermal environment, a controlled, sustained nuclear chain reaction is not only possible, it actually makes a lot of sense. Add to that modern drilling methods, proven heat extraction systems, and modular manufacturing, and we've got a new business model for nuclear. Fast to deploy, inherently safe, and economically viable. So what makes this solution so special? Well, first, the geology for us does the heavy lifting. At 1 mile deep, the pressure of our system is about 160 atmospheres, which is exactly what you want inside a surface level pressurized water reactor, which means we don't need heavy, massive forgings for reactor vessels. The Earth provides what conventional engineering has to build. Second, the rock itself becomes our containment structure. Traditional nuclear power plants at surface level require massive concrete containment domes, and these things can cost billions. For us, billions of tons of rock provide passive protection. No surface containment dome required. Third, we use natural circulation for reactor core cooling, eliminating the need for pumps or passive safety systems. The borehole is filled with water, and that mile-deep column of water serves as built-in heat sink, alleviating loss of coolant scenarios by design. And fourth, we're not building mega project at Deep Fission. We are drilling holes. We can drill, install, and commission a unit in under 6 months. Now compare that to years of construction timeline for surface level reactors. Our approach borrows from industries. Oops, I forgot about my deck. Okay. Our approach borrows from industries that have already scaled. Oil and gas for deep drilling, geothermal for heat extraction, and modular manufacturing for our reactor canisters. In short, we are not trying to reinvent reactor physics, just how we deploy it. And here's a key point that differentiates us from many other advanced reactor technology companies that you may have heard of. We use light water reactor physics, the same technology that's already operating today in hundreds of reactors worldwide. And we use standard pressurized water reactor fuel assemblies enriched just below 5%, which is commercially available uranium today. We're not betting on new and unproven reactor designs or materials. We're not inventing new exotic nuclear fuels. We're not waiting for licensing precedent for all of that. And we're not requiring highly enriched uranium. Instead, we've chosen what already works today and we are focusing on how to deliver it better. All this brings me to the most exciting aspect of our design, which is its impact on cost and economic advantage of our system. Because the pressure inside and outside of our system is equal, it means that we don't need massive heavy forgings for our reactors. We can use thin-walled rolled steel to manufacture our reactor canisters. We are also eliminating most of the expensive surface level infrastructure. As I said, no containment domes, no massive concrete pads. All of this represents the bulk of upfront costs for nuclear energy projects. And for us, it's provided by geology for free. And because our reactors can be factory built, we can take advantage of standardized manufacturing, which allows for consistency, quality control, and volume-based cost reductions. So not only we are trying to deploy nuclear better, we also want to make it affordable and bankable. So each of our reactors, one unit, generates 15 megawatts of electricity, with one unit enough to power about 10,000 homes. But our system is modular, which means we can scale to meet customer needs. This is great for powering data centers, military and industrial loads, as well as remote communities and microgrids. We can build hundreds of megawatts of baseload power on only a few acres of land. No other small modular reactor approach has this kind of siting flexibility combined with deployment speed, fuel supply chain alignment. By using standard low-enriched uranium fuel, we alleviate fuel qualification delays, accelerate licensing and supply chain development, and accelerate deployment at faster speed and lower risk. So where are we today at Deep Fission? We've been selected by the US Department of Energy to participate in their reactor pilot program. Oops. Keep skipping. Our target is to demonstrate our technology and our first reactor by July 4th of 2026 via this DOE demonstration reactor pilot program by next year's Independence Day. We are self-funding this project with funds we've recently raised, and we already actively engage with the Nuclear Regulatory Commission to prepare for submitting our first construction and operating license. And our goal is to transition from the DOE authorization of the pilot project to commercial fleet and our first commercial project online by 2029 timeframe. And we've partnered with Endeavor, a global data center development company, to deploy 2 gigawatts of deep fission powered capacity at their data center sites. All this to show that we are not a lab experiment. We have a clear path to commercialization of our technology. Many people think nuclear has a perception problem. I think nuclear has an execution problem. In this country, we've discovered and proven nuclear physics, but we haven't proven that we can consistently build it on time and on budget, or that we can adapt it to modern power needs. At Deep Fission, we're not trying to change what makes nuclear great. We're trying to change what makes it hard. We are replacing concrete with geology, forgings with manufacturing, centralization with modularity, and delay with speed. In short, we are rethinking how nuclear is delivered, not what it is. In my final thoughts, I'd like to end where I began, with a young girl who grew up in Ukraine, afraid of nuclear energy. But today I stand here not with fear, but with conviction that nuclear energy is essential and that we can deliver it faster, safer, and more practical than we've done in the past. I truly believe we are entering a new chapter of nuclear energy, the one that's based not on ideology or nostalgia, but the ones based on engineering, economics, and execution. Today, we need power that is reliable, scalable, affordable, secure, and actually deliverable. So that's what we're trying to do at Deep Vision. Thank you. I totally forgot to go for my deck.
You're fine. No, that was amazing. Wow, thank you so much. I actually had a question, if you don't mind, and asking some questions. So the test reactor that is going to be installed by July of next year, what is the size of that? Is that your commercial size, or is that small?
So we're going to try to put 4 fuel assemblies in there and try to make it the size of our first commercial project, but we may not generate 15 megawatts for this demonstration project. But the plan or the goal is to transition that pilot program project into our bigger commercial project when we get the NRC licensing.
Very good. Do we have any other questions in the audience? Yes.
I'm just wondering about your location and where you will be building your project.
So our solution is pretty flexible when it comes to siting, but we are working very closely with 3 states already, which Utah is one of them. We're also looking at Kansas and Texas. We haven't publicly announced yet the precise location of our first project for this reactor program, but it's likely going to be one of those 3 sites.